Okay, let's get into it. For our deep dive today, we're looking at one very specific piece of hardware, the Thor Broadcast FRFRXRM. It's a CATV RF fiber receiver.
Right. And our whole mission here is to figure out that translation process. You know, how cable TV signals, which are RF, get turned back into RF after traveling as light.
Exactly. We're looking at that endpoint interpreter, the box that takes light and makes it, well, TV again. We're talking about that familiar 45 to 870 megahertz signal.
And this is for the big jobs, the kind of stuff you rack mount and just expect to work flawlessly.
So something that jumped out at me right away is the wavelength flexibility. It works with either 1310 or 1550 nanometers. Is that just a nice-to-have feature, or is there something more fundamental going on there?
Oh, it's fundamental. It's all about architectural assurance. It means you can plug this thing into almost any existing high-end fiber network, whether it's built for shorter runs, which is usually 1510 nanometers, or the longer haul stuff at 1550 nanometer.
Got it. So it's built to be compatible from the get-go. Now, once it accepts that light, it's all managed by a microprocessor, right?
Right.
I see it's got an LCD screen for status, faults, all that. But what's the one feature that, really guarantees that the signal stays stable?
That would have to be the optical automatic gate control, the AGC.
The AGC.
Yeah, that's the device's safety net. When you're dealing with fiber, the incoming optical power can fluctuate. The AGC automatically adjusts for those dips and peaks. It guarantees a rock-steady RF output. Without it, your signal quality would just be all over the place.
Wait, hold on a second. If the signal is just light, why does it even need an automatic gain control? I mean, doesn't the light just arrive?
That's a great question. It's because we're not talking about a pure digital 1 or 0 signal. It's an analog RF signal that's been modulated onto the light. So if that optical power level drops even a tiny bit, the conversion process introduces noise. That electronic snow or hiss you sometimes see. The AGC just makes sure the power level's perfect before conversion.
Okay, that makes so much sense now. But for me, the most fascinating detail in all of this is how all that tech depends on something so physical. The connector. The source material practically calls it a trapdoor if you mess it up. Tell us about this SCPC requirement.
This is, absolutely crucial. The receiver requires an SCPC connector. The A stands for angle polished.
Angle polish?
Right. Think about it this way. If the tip of the fiber is perfectly flat, like on an older SCPC connector, some of the light hits that flat end and reflects straight back down the fiber. That back reflection is a disaster. It just corrupts the incoming signal instantly.
So the angle is literally there to act like a deflector, to bounce that reflection away from the signal path.
Precisely. The angled polish makes sure any reflected light gets sent harmlessly into the fiber's cladding, not back toward the source. So if you're trying to plug this into an older system that uses flat connectors like an SC, ST, or FCPC, you absolutely have to use an optical jumper to make that conversion. If you don't, you've just ruined your broadcast quality.
That's a powerful lesson. Okay, shifting to performance. You said this is professional grade. What are the specs that tell you this isn't something you'd buy at a big box store?
You're looking at figures like the CNR, or carrier-to-noise ratio. Over a 10-kilometer link, it's greater than 50 dB. That's incredibly clean. It's what you pay for. It means basically 0 electronic hiss. And that's backed up by very, very low distortion figures. The CTB is below negative 63 dB, and the CSO is below negative 57 dB.
And to put that in practical terms for everyone listening, those low numbers mean you get no ghosting in the picture, no weird lines, no interference between channels. It's a flawless picture after a pretty long journey.
Absolutely. And just to round it out, the box isn't dumb. It has network management ports, RJ45 and RS232, and it speaks standard protocols like SNMP. Plus, it's tough. It'll operate from below freezing up to a really hot 65 degrees Celsius.
So when you put it all together, this deep dive really shows how one unit takes light and turns it back into a perfect, reliable RF signal. And its success depends just as much on tiny physical standards as it does on smart electronics like the AGC.
It really does. And it raises a bigger question, doesn't it? If a simple thing like the microscopic angle on a connector can make or break a high-end broadcast signal, what other invisible hyper-specific standards are out there governing all the data we rely on every single day?
Something to think about the next time you switch on the TV. That's all for this deep dive.